Userspace networking fact or fiction. He's a Linux developer who specializes in kernel networking issues, and he's sometimes a network plumber. Up to you.
Thank you. And since everybody made the trek over here, the best question I have a prize for. You may wonder why someone whose livelihood is working on Linux networking would advocate you not use it. We actually have the best, most complete, highest performing networking stack in any OS. But there are times when people just want to do things outside the boundary. This graph shows packet size on the bottom and how many packets a second that means at the top. And the blue line there is at 10 gig. So at 10 gig, in order to keep up, you have to process 14.8 million packets a second. The yellow zone is where Linux is able to keep up with normal Intel CPUs, modern generations. That number varies between 1 million to 500,000 packets a second, depending on how you tune and what you're doing and what else things your application has going on. So if you're in the yellow zone, I recommend you stay with Linux networking. Don't even consider anything I talk about in my talk. It isn't going to help you. But if you're doing something outside that zone, you're outside the edge, then some of the things that I talk about might be of interest to you. And these are, what I'm covering is 3 different solutions that different people have made. I'm not advocating for any one of them. Most of the information and all the performance numbers came from those people. So they're not mine. I put that in because it's a kind of a marketing disclaimer. It's like if I'm writing a car review, I'd like to know that the car does 0 to 60 instead of 0 to 55 in 3.5 seconds. So because I haven't measured any of these, I don't want you to pick on me. But we wonder, why is this a problem? Well, where we normally talk about servers, 1.2 million packets a second, you have about 835 nanoseconds between packets, which comes out to this many cycles and this many cycles on a 2 gig and 3 gigahertz process. When I was here 7 years ago, Paul McKinney gave a talk about RCU and cache size, and he made an example about the difference between an L3 hit and miss, and he did with toilet paper up and down the aisles in the big theater. The point is, you got 40 cycles if you're staying in the cache, but if you miss, it's about 200 cycles. So sure, you can do 12 cache misses in your software and you'll be fine and you can keep up. If you start to do things over here, you start to handle 64-byte packets. You can do the math to get down to, gee, 1 cache miss and you can't keep up. There's many cache misses in the normal Linux stack. You can't help it. So you can't possibly do that. And when I say the traditional Linux stack, what I'm talking about is you've got an application running Userspace, nice generic API sockets, a TCP IP protocol stack, processing and ordering your data and maintaining its consistency, Ethernet drivers, and down here you have the network interface and hardware. Looks like a simple picture, but if you actually look at the real packet flow, this is actually from Wikipedia, and the NetFilter guys did it, but you start to see there's all these features where we start out and we decide to have rules to mangle, and we have things in optimizations that occur, like packet aggregation for receive a GRO, and we have deferred interrupts, and there's many, many pieces we've created to make a generic solution. If you want that generic solution, and chances are you may need it if you're running a server on the internet, you want a firewall. If you on a server on the internet, you may want to run Wireshark. If you're on the internet, you may even want QoS things like I'll be talking about tomorrow in buffer bloat. All those features are part of this big, long chain. There have been people that have started on this before, the TCP offload engine guys. But their view of the world was, we want to sell you expensive hardware with proprietary firmware, with proprietary TCP stacks, and we'll just do some socket glue so that your application is the same. This got roundly rejected by the networking community in Linux for several reasons. Part of it was all those features like firewall and security, there was no way to put them in. But mostly, this was just a big blind spot. So if something came along, or you wanted to change something, you wanted to change how queuing was done for buffer bloat, or there was a IPv6 hole because some packet ordering, you had no ability to change it. It was basically Linux running on top of proprietary software. And the solutions that I want to talk about don't do this, although some of them are coming from the same genesis that caused this to occur in the first place. The other thing is, to be honest, in the process, we've done a lot better. When this was popular, the Linux kernel was a fair degree slower. And there have been many people that have worked a lot on reducing the cache misses, improving the lookup, improving the scalability. So several of the things that were an issue in the early 10 gig days are no longer an issue in the server market. So you decide you want to brave it and go on your own. You want to do user mode networking. The first possible way to do it is open up a raw socket, get the packets, do it yourself. And there are people that write protocols to do that. I don't recommend it. You aren't going to get very good performance out of it, but you do get raw access to the packets. And I actually do some things like that to create testers to test protocols. For example, well, I don't do it at that level a lot of times, but for example, testing BGP protocols. People fake BGP by doing applications. The other one is there was a set of projects, you may have heard of PF Ring and AF Packet, where you can get better, faster access by using memory maps. You still don't have direct access to the hardware. You still have the layering and delays of that. But it is a little more general. But once again, you've stepped out of the realm of general purpose operating system. You've all of a sudden have to bring in some kernel patches to do that. And lastly, if you want to do it, there is the option of you can just say run everything in the kernel. In 2.4, there was a kind of semi-serious version of an HTTP server that ran in the kernel that gave the great web benchmarks. But that's probably not how you want to support your product, and there's definite advantages for the isolation. So the first one I want to talk about is something called Open Onload that SolarFlare did. And this only works on their hardware. And what they did was they took the traditional stack and they put another piece, and they split the protocol so there's a kernel part and a user part, and they have a shared memory interface between the two. So they keep the generic stack in place for the connection establishment and all those parts, but then they basically go into high-speed turbo mode later on once the connection's established. The cool part about this is they offer a socket interface, and you don't have to change the application at all. You do an LD preload, you get their shared library, and you open sockets, and it just looks like a TCP connection. Even more complicated, and you really should go see the Google Tech Talk on this, they dealt with all the nasty semantic issues. In Linux, you can have things like a file descriptor open, and you exec another process, and you have to inherit that file descriptor and its TCP state, and namespaces, and forks, and all those pieces, and how much trust you want to have between the other process that you just gave it and you've got two instances of the shared library and they've got the same connection. It's quite a complicated feat. And the whole set of software is available as a big GPL project. The thing that they do, and I'll go into the performance details, is they cut down the time that's spent in the kernel. So for normal packets, it's 0. It goes right to Userspace. This is sort of a walkthrough of how they do it. This is a normal application socket hardware drive. This is their picture of that picture I had. User level, they talk about the way it works is they use the fact that the SolarFlare hardware, you can provide vNICs. So for each application, you basically give it a separate virtual NIC with its own MAC address. So that's how they do the multiplexing. And the user level process gets a view of the receive and transmit rings in the hardware and the shared states going on between the kernel and the user mode. And these are their benchmarks running RHEL 5. And you start to see why this shows up. If you do kernel, round trip, ping pong, on TCP, you get 11 microseconds. Hardware can do 4, with they're doing 5. So they basically have half the time for a round trip application. And where does this get important? All those guys doing financial trading. You save microseconds, you just made money over the other guy. And the CPU overhead is also important because basically they're spending less time. You cut out a copy, you cut out a wake up. It's all done in Userspace. This one is a graph of, the red line is open onload with one CPU streaming data, and the bottom is the kernel streaming data. So basically, when they get up to full-size packet message size, the kernel's only able to get half of a 10 gig streaming, and they're able to fill a pipe a lot sooner and faster. It gets a lot more interesting when you talk about UDP with single packet request response situation. So this is the low end of that million packets a second number because they're going to Userspace, 473,000 packets a second, and they can do 2 million. You see this one is basically, they're showing that the kernel version doesn't scale for them, but they can scale the version in Userspace. The UDP side also, the number of messages a second, at this point, the point is that they keep scaling up here up to 1600. The kernel with one CPU is dying on the red line. With 2 CPUs, it's maxing out at about a million messages a second. So I was interested in this, but to be honest, for anything I've been doing, I do have some demo boards, but I haven't actually got it running. It's very specific to their hardware. It requires their hardware. They have a GPL v2 open source project, and they have a very long, hour-and-a-half Google Tech Talk if you want to find out all the details about all the internal implementation things to do the TCP. The next version I want to talk about is NetMap. NetMap is done by Ligio Rizzo of University of Pisa in Italy. I just got in contact with him because he's actually on sabbatical at Google for a month, so I'm going to go down there and visit him. It was a BSD-based project to start with, but there's a port to Linux. And I'll talk a little bit more about the issues with the port later. It has very good scalability, and it offers a raw packet interface, but it can also be used with libpcap, which is the standard packet interface. The way NetMap works is it provides an abstraction of the NIC ring. So the ring buffer in the NIC that's used to hold packets that are transmitted, and then what packets coming in that are received, it basically makes that available to Userspace. And how it does that is the application opens the device dev netmap. It then does a special IOCTL to say it wants to connect to this interface, and then it maps the ring buffers. And on transmit, it fills those ring buffers and gives an IOCTL to wake up the actual NIC hardware. On receive, it can poll to see if there is packets available. More interestingly, you could also use the standard Linux poll and select logic, so you can write a multi-threaded application. You can decide how you want to do your threading model based on that. There is no protection here. There's nothing that says, there's no locking of those ring buffers. So it's up to your application to either do user levels locking or dedicate a CPU to that particular queue. And the netmap is multi-queue, which is actually kind of surprising because BSD is pretty far behind on their multi-queue support. But you can open and bind a particular FD to a particular ring buffer. All the 10 gig, well, I wouldn't say all, but 99% of the 10 gig hardware out there supports multiple queues, so to get scaling. And so you can say, I want this thread, I have this FD open, I would like to bind it to this queue, and I would like to transmit packets on this queue, and I will poll for it to receive on this queue. It leaves all the affinity, all the locking, everything up to the application. It only provides the actual access to the ring buffers. What's interesting about how he implemented NetMap is it's done as a small add-on to the actual device driver. So, for example, the Intel 10 gig Ethernet driver, it's about 8 lines that get inserted to say, check if user mode networking ring buffer is enabled. That means that all the management of addresses, counters, everything else, the interface looks normal. It's just being used differently by the application. And that also means that it's perfectly possible to send and receive and use that interface for both normal traffic and, well, what we in the networking world call slow path traffic, stuff that goes out through the other side. And this is his performance graph. Basically, the bottom is running packet gen on Linux, and this is CPU clock speed. And if you look with a modern CPU, somewhere between 2 and 4 million packets a second is what you can get out of the Linux kernel packet gen. And the demo application he wrote from NetMap is a version of a packet gen-like process from Userspace. And he can saturate it with a fairly low-end CPU. And on the receive side, it can keep up with a 10 gig interface. But that's just sending, receiving packets. That's not doing it. You have to compare it slightly with the earlier case where we actually had TCP and UDP. This is just, you got the packets, up to you. And if you look at where this is interesting, comparison, there's really three kinds of forwarding that go on now. There's bridging, there's the new Open vSwitch, and there's actual routing. And his implementation, what he's measured is bridging and Open vSwitch. So if you see actual BSD and Linux, you're still about 0.6 or 600,000 packets a second is what you can get through. And with NetMap, and he did 2 versions of, one is using libpcap emulation, and the other one is using NetMap directly. And the PCAP emulation adds overhead, but basically you can keep up packet forwarding with netmap, bridging, or in this case, you're starting to see the overhead of Open vSwitch. I mentioned that it's BSD based. The Linux port of it does exist and you can download it, but it's kind of in the super ugly state, the state where it would go in the staging tree. Things where they go pound define, mbuff is skbuff. It's sort of BSD code, cut and paste, put into Linux. And I'll get into a little bit of that later. Another one I'm very familiar with is the Intel DPDK for Data Plane Development Kit. And this has been around for a while. They just released it to the public in December. You can download it from their website. And the way it works is the application actually has the Ethernet driver itself running in Userspace. They use UIO to unmap the normal device, map the PCI resources into Userspace, and so the Userspace application is at the Intel hardware. And you have code that looks very similar, same code base, in the DPDK that's running in Userspace to talk to that hardware. Yeah, too busy Intel slide. The thing that this is, you have to understand that this came up, I wasn't involved, but it came from companies that were doing real time and were doing bare metal. So a lot of the infrastructure and a lot of the environment this provides, there earlier was a version where the actual threads were running on bare metal. Turned out that supporting the threads on bare metal was just too painful for the amount of gain. I mean, the Userspace scheduler stuff has gotten to the point where an HPC application is not disturbed enough that you can just run as a HPC application. And in the DPDK, what it does is you go do a bunch of setup, and then after the setup, it spawns a bunch of threads and does all the affinity for you and binds them to the CPUs. So the actual API includes a whole set of thread management and thread libraries. And they call this the runtime environment abstraction layer. And really it comes down to you're abstracting running in Linux versus running on bare metal. And since this is a source code product and it's statically linked into your application, it is BSD licensed. And it has to be BSD licensed because if you're going to produce a proprietary application, you need to be able to do it. Link to it. And they also give you a whole bunch of libraries that provide features you would need if you're writing something that processes packets. So, for example, they have a lock-free ring buffer. They have memory management. All in order to do DMA in Userspace, you have to do it from fixed memory that has a physical address that is visible. So they provide memory pools that map to the huge TLB pages and give you the, give me some memory, tell me its virtual address, tell me its physical address, because you may need the physical address to talk to the actual hardware. They also provide spin locks and reader-writer locks and all the other things you need to mutex your application because, once again, you're getting raw access to the hardware. The device drivers give you exposed queues. So you have packet queues to send and receive packets. You do not have a nice, safe, I can have any thread send a packet on any queue. It's up to you to reserve one CPU or provide locks when accessing that queue. Likewise, on receive, the interface is get me a packet from a queue. And it's up to you to do the threading model to decide how you want to do that. Oh, why would you want to do this? Once again, massive performance gains, small packets. They can get 20 million packets a second. with the demo apps, and they give you a demo app that does level 2 forwarding. And this compares, basically the blue line is the DPDK. You can also run this under KVM or VMware and pass through a device, a virtual function device, to the application. But we're on the bleeding edge of this, and because you're on the bleeding edge, you're going to put huge demands on the bus. And it turns out that with the current generation Intel architectures, you don't get full speed on a virtual function device. And they're working on that. That's why they've got the boxes. As you can see, though, out here, full-size packets, there isn't a lot of gain. So unless you had some particular reason that you wanted raw access to packets, there isn't a huge gain. If you look at these three, each one of them provides a different level of solution. But they all are open source in some sense, and each one ends up needing some kernel support as well. You can't just plop it in, run it on RHEL. You have to, in the NetMap case, you have to basically have the NetMap API. You have to have the small change the driver. The TPDK case, you need the small UIO shim driver that is used to access the resources. And Open Onload actually goes and changes the TCP engine to deal with the sharing. The hardware support, SolarFlare supports Open Onload. The DPDK runs with Intel hardware, but they aren't adverse to getting other vendors to support. The problem is other vendors, it isn't popular enough for other vendors to get involved yet. NetMap, Luijo has got it up running on Intel and Realtek and wants to get it running on other ones. And if it was farther along, it wouldn't be a major issue. It's kind of like, if you're familiar at all with, we just recently added byte queue limits to Linux. And to support it on the faster hardware required a small change to each driver that supports it. And it's not that there's actual, unlike the DPDK, which has full knowledge of the hardware, with NetMap, there isn't that. The big issue with all this stuff is it's out of tree code. So if you have a production system, don't do it. If you have a engine, a firewall engine, a routing engine, a bridging engine, and you're shipping something that is a packaged product, you're already dealing with creating your own kernels and dealing with this, it's no big deal. If you're dealing, as far as resource sharing, all of these basically are high-performance applications. They monopolize the CPU. They may monopolize the network interface card. They're not friendly. They're not running in a normal environment. And lastly, you're basically throwing away security to do this. There's no firewall. The Intel DPDK right now does not have any DMA isolation, so you're basically running the Userspace driver and you're asking it, you're trusting it not to do bad DMA. The NetMap, you're at least only mapping the ring buffer, and you're only trusting it not to screw up the ring buffer. And the Open Onload has done a better job, but they're at a higher level, so it's a little more complicated. And also, all this stuff won't play well with the work that has been done to do trusted sockets and the labeling and all that stuff. You're basically throwing that out the door too. So back to that earlier diagram with all the layers and pictures, you're throwing it away and you're going to end up recreating what you need out of that picture. So don't trust the performance numbers you get from the vendor. It's like looking at engine horsepower ratings. What do I think is needed in this area? I think NetMap, being the non-vendor portable one, is probably the most likely long-term solution, but we really need a Linux version, not a port. And after that, I think we'll need to have some higher level protocols on top of it, because send and receive packet and libpcap is not a general purpose solution. The Intel DPDK, what? Rusty?
You don't need this, but it's a really good solution for virtualization.
Yeah.
When you're dealing with actual packets.
Yeah. With the DPDK, Intel's talking about wider device support. You could go ask them, and they've got a bunch more features that they're adding to it. And I've got some NDA stuff, so I didn't want to worry about what is an NDA. And Open Onload is an active project from SolarFlare. And if you're interested in digging deeper, the first place to look at is there's Google Tech Talks. There's one on Open Onload. There's one on NetMap. And I recommend you go look at them and dig down a little deeper. On the DPDK, it's new. Intel's got a fair amount of marketing documentation, and there's been a few people, one of the guys I know over in Japan who's also investigated it as well. With that, since it's lunchtime and I'm getting the 10-minute sign, I thought I'd end a little quickly. And remember, the best question gets the prize. Yes?
So with all that, have we... So is there much new research going into actually looking back at TOE, maybe using some of the newer network processing to make it a more, maybe just a less horrific
I think...
hardware?
Is this on? Okay. What I've seen is that the trend in hardware has gone the other way, that the hardware guys have invested more in doing how can I virtualize my hardware better and how can I do tunneling. They haven't invested in, the market didn't accept it. So if I'm a company, I make what my customers want, and my customers want more virtualization. I mean, like Intel on 40 gig, we just put a bunch of stuff on how can I do VXLAN and GRE tunnels and make the hardware magically do it for me. So that's where they're investing.
Do you see a lot of people using the packet mmap interfaces outside of PCAP? I mean, I've used that.
I've never seen anybody using it outside of PCAP, but I'm sure there are people that...
I've used it. I mean, it actually...
Me too.
But I'm curious. I've always been curious what the performance against something like SolarFlare would be, but I've never actually had the time or the resources to do it.
I don't know. I guess the people we also see are people that are doing NetFlow and stuff like that.
The packet mmap still serializes a packet out of skbuff and copies it into Userspace. So it's still an extra copy and things instead.
I worked on a product a couple of years ago where we actually were getting 10 gig line rate using proprietary code in Userspace, so it works.
So one obvious place where they want to push packets directly to and from Userspace is virtualization, QEMU, KVM, etc. So have you looked at the solutions that we've hacked together for that by comparison? Because it's a similar kind of problem.
No, I haven't actually looked at that. Although I will admit that I have looked at what it takes to do VirtIO type drivers in these environments.
Yeah, so I mean, the obvious one is vHostNet, which is still labeled experimental until that patch goes through that flushes all those out, for I think quite a good reason, and I've actually been looking at that recently, and it ties in really well. If we have one direct Userspace solution, it's the obvious solution to feed into that kind of mechanism where you've got a virtual machine is the process. Then you don't have to worry about re-implementing TCP because you've already got that inside your VM.
Yeah. I'm also a little bit concerned, though, that just like every time we get a new feature, it exposes bugs in existing device drivers, that we may find that this exposes bugs in the existing device drivers where they're not up to full speed as well.
So as we move the host layer more towards packet passing, as you said, you're moving away from TCP offload. Does that mean we're losing hardware checksumming and segmentation and all that's like something we're just never going to get back?
No, most of these solutions basically pass that metadata with the packet because you end up with some amount of metadata you want anyway for VLAN offload and TCP offload. So invariably, for example, the Intel one, you say receive packet, and you get packet plus metadata.
Right.
In their case, it's an MBUF form, and likewise with NetMap, there's no reason we couldn't have ability to give you the packet data plus here's whatever else the hardware can tell you. For another one, an example would be timestamps. A lot of the hardware provides timestamps now. And I could see if I was doing a financial trading application, I want to know when that packet arrived, and that's part of the metadata that's there with the hardware.
With reference to the questions about TOE and so on, am I right in thinking TCP isn't in the problem space here at all, because your graph shows that for full packets like you might do for a TCP file transfer, there's no difference anyway, and this is really about UDP round trip
really,
time?
I mean, like I said, it's really about UDP, although one could argue that if you were doing the problems of TCP are scale problems. So if I was doing a huge web server with millions of customers, then maybe I'd want to do it. But the people who do that have clouds and they just spread it out anyway. Yeah, but you do it the other way, right?
If only I could say we just had clouds and then
Yeah, I know.
Any other questions?
Yes. I'll be around this afternoon, and I do have some other stuff that old gadgets people want, so if they want to get a hold of me for that. And the award for the best question, I will go with the first question because it was fairly good, and you get the card reader. Thank you.